Let's discuss the runtime of a recursive function now. Now this time we're going to start with the intuition first, and then we'll do the exact count just to mix things up. And so what I'd like you to do is, given this function f3, give it a chance, give yourself a chance. I mean, you can't give this function a chance, it has no agency, but give yourself a chance to look at this function and think about what you think its runtime might be. First, figure out what it does, and then two, what do you think its runtime will be? Okay, so if you're someone who took 61A, this should be familiar to you as what is called tree recursion. And so if we look at this diagram I have in the corner, you may have noticed, we can see that if we call our function f3 with, say, 4, we end up with 2 calls of with the input 3, and then in turn f3 of 3 makes 2 calls to f3 of 2, and those in turn make 2 calls to f3 of 1. So we end up with a tree of calls, as shown here. And what's very notable about these calls is that if we now go up to n equals 5, we're going to basically double the amount of work that we have plus 1. So the overall runtime in this case will be 2 to the n. Every time we increase n by 1, we double the work, which is exactly 2 to the n. Now that was an intuitive argument, something good enough for us in this course. But if you wanted a more rigorous, more mechanical, more algebraic solution, we can also do that too. So let's try that out in 2 ways. I'm only going to go through the details for the first, but there'll be a second algebraic approach if you'd like. So the first is, let's just count the number of times that f3 gets called. That's going to be our cost model. Okay. So in this case, if we call f3 of 1, there's only 1 call. If we call f3 of 2, well, there are 3 calls. The one with 2 as an argument, and 2 with 1 as the argument. If we now go up to f3 of 3, we have 1 call for f3 of 3, 2 calls of f3 of 2, and 4 total calls of f3 of 1. So let's continue that pattern. What would be if we write out the entire expression for c of n? It's going to be 1 plus 2 plus 4. Your job now is figure out what's the last term in this sum. So think about that, and I'll give you my answer in a moment. And here's where I think considering specific examples will help you. Okay, so let's take the example we have right here on the slide. We say in that case, n equals 4. Okay, what's the total number? Well, it's 1 plus 2 plus 4, and then how many are in this bottom row? 8. Okay, how can we relate 4 and 8? Well, it's going to be 2 to the power of 4 minus 1, right? 2 to the third, which will be 8. And so we imagine that if we now move up to n equals 5, the last row will be 2 to the 4. If we have 6, there'll be 2 to the 5 calls to f3 of 1. And so forth. And so in the end, our final term in the sum is 2 to the n minus 1. Okay, great. So now we've got an expression for the total number of calls to f3. So what I'd like you to do now is give a simple expression. Okay, so it turns out, in the previous video, we talked about this. We do know how to sum the first powers of 2. In particular, the exact result will be 2 to the n minus 1. And why? Well, this is the sum of the first powers of 2 that we saw from before. And I'll just walk you through the math again, but it's nothing new, right? So as we know, the number of calls to f3 is going to be 1 plus 2 plus 4 plus 8, all the way up to 2 to the n minus 1. And we also know that the sum of the first powers of 2 from before is going to be 1 plus 2 plus 4 plus 8 plus q, where q is a power of 2. If that is the case, that q is a power of 2, then the exact result is 2q minus 1. Now, since in this case, basically we say that q is 2 to the n minus 1, like that's the power of 2 that we're thinking about, then we have that c of n is 2q minus 1, which is 2 times 2 to the n minus 1, all minus 1 because of this expression here. And therefore, the overall result, if we multiply out our 2, is going to be 2 to the n minus 1. Okay, just as we said here. So that's it. We've now found the exact count. And as a result, since the number of calls of f3 is 2 to the n minus 1, and the amount of work during each call is constant, then the overall runtime of the function is going to be big theta 2 to the n. So that's the algebraic way of putting it. Now lastly, there's also an approach where we can write out what's called a recurrence relation. In this case, we say, okay, well, c of 1 is 1. What's c of n going to be? What's it going to be if we... This is really digging into the recursion. Well, C of n is just going to be 2 times C of however many times we do it 1 level lower plus 1. In other words, if we think about how we went from this tree to the larger, where n equals 5, we doubled the size of the tree, and then we have that extra call for the root. Okay, so given this recurrence relation, you can actually also solve this, but this is a little more technical. And so I'm not going to show you how to solve it in this video. I'll put the slide up, and it's also available on the website if you want to go check it out. So in this case, if we want to count the number of calls, we can work through some algebra here. But again, I'm not going to say anything about it because I think our earlier technique is more intuitive, more to the point, and just better in general. But this is an alternate approach if you'd like instead.